In this context, let us understand the meaning of inductance and the materialistic property. The inductance, it is inducing something when there is a change in a material. When there is a change in the material, some change in the material, there we see something is induced in it. This induction is to resist that change what is taking place in the material. That is called as inductance. It is a property of the material. This inductance is electrical inductance. It is inductance in electrical conductors. Let us understand the meaning of this inductance in this electrical conductor. There is a conductor which is in the coil form. This is also known as solenoid. As you know, solenoid means there are number of turns. That is, number of turns. That is the shape of the solenoid. When a current is flowing through this coil, this flow of current, as you know, produces magnetic flux in the coil. That is, magnetic field is passing through this coil. This coil has a number of turns. The total magnetic field passing through the coil is called as magnetic flux. And we give the symbol that is pi for the magnetic flux for a single turn. There are a number of turns. Pi represents a symbolic representation of magnetic flux for a single turn. In the coil, there are n number of turns. If there are n number of turns, what would be the total flux? That is, flux through all the turns. Magnetic lines of force passing through this coil, that is the total magnetic flux, is n into pi. The magnetic flux is induced in the coil. When the current is flowing through the coil, magnetic flux is induced in the coil. That magnetic flux is n into pi, total magnetic flux. And the magnitude of this magnetic flux is directly proportional to the current, amount of current flowing through the coil. Direct proportional to the amount of current. More magnetic flux is produced in the coil. Less current, less magnetic flux produced in the coil. If you replace the symbol by equals, that will take a constant. The constant, proportionality constant, is called as coefficient of self-inductance. Why it is self-inductance? Because inductance in the same coil, current in the coil, and inductance in the same coil. That is called as self-inductance. This L stands for coefficient of self-inductance. This equation represents that magnetic flux induced in the coil is a function of L and I. L is a constant, depends on the coil. It is related to the parameters of the coil, L. Now the question is, As long as the current flowing through the coil remains constant, the amount of current or the strength of the current flowing through a coil remains constant, magnetic flux also constant. Constant current, constant magnetic flux. Of course, this amount depends on this amount. And interesting point is here, if the current is varying in the coil, changing in the coil, intensity of the current if changes in the coil, changes with time in the coil. The varying means the current either may increase or decrease in the coil. Increase or decrease, variation. Any continuous increase in current or any continuous decrease in current. If that happens, variation, very important, variation of current in the conductor. If that happens, what will happen to the magnetic flux? Magnetic flux also variable. If current is variable, magnetic flux also variable. Magnetic flux changes in the coil. As you know, as magnetic flux changes in the coil, any variation of magnetic flux in a coil like this, in accordance with the Faraday's law, what happens? When there is a variation of magnetic flux in the coil, there induces EMF, that is epsilon or E. Any variation, if this as long as constant, there is no current, and then the voltage is induced in the current. If there is a variation of current, EMF is induced in the coil. That EMF in the coil, induced EMF, it is also called as back EMF. What is back EMF? Back EMF means it is the EMF in the backward direction. EMF which opposes the applied EMF. It is because of the applied EMF current is flowing. Any variation induces EMF in the coil which will oppose that EMF applied, or it induces current, that is called inducing current, which will oppose the variation. That is the idea is here. Faraday's law. So the same thing what I said now, that is the mathematical equation for the current and magnetic flux, they are related in this coil. I said if there is a variation of current, there should be a variation of magnetic flux. If that is the case, you have to, that is a variation with respect to time. Therefore, this equation need to be differentiated with respect to time. For a variation, we have to differentiate the equation with respect to time. So, variation of current with time means variation of magnetic flux with time. So, left hand side, differentiation of left hand side, differentiation of right hand side. Differentiate with respect to time, differentiate with respect to time. That is d by dt of this. And about the coil, for a coil N remains constant, that is number of turns remains constant, and L is a constant of this coil. So these two are constants. After this, what is that? N becomes N into d pi divided by dt and L into di by dt. That is after differentiation. It is only variation of I and pi. L and N remains constant. They are constants of the coil. The final equation after differentiation. And this value, what is that? I already told a mathematical form of Faraday's law. That is, any variation of magnetic flux in the coil induces EMF. It is same as it is epsilon or E. In some books we are using epsilon as a symbol and E as a symbol. That is induced EMF in the coil minus because of back EMF. EMF in the backward direction. So minus E equals L into di by dt. This value is E. So this is in accordance with Faraday's law. Let us see how does the induced current or induced EMF changes the variation of current. There are two types of variation. One is increasing current or decreasing current. Increasing current in the conductor. This is increasing current is also called as growing current in the circuit. Current is growing if the current is increasing the circuit. If the current is decreasing in the circuit, it is also called as decaying of current. Current is decaying in the circuit. If the current is growing in the circuit, if it is continuously increasing in this circuit, what happens? I told you, EMF is induced in the circuit and also the corresponding produces, any EMF produces its own current. It is called induced current. This induced current and induced EMF will always resist the change taking place. What is the change here? Increasing. It means, so this current, induced current, will oppose the growing of current in the circuit. How it will happen? How it opposes? By flowing that current in the opposite direction. So if the current source of current is flowing in this current, induced current in the coil will flow in this direction when the current is increasing in the coil. That is what induced current will oppose that change. If the current is decaying in the circuit, suppose the current is decaying in the circuit, see that current is decaying, it also induces EMF and also its own current, induced current. These two will oppose this change, resist or prevents the decaying of current. It will oppose the decreasing current in the circuit. Decaying, maintains what is prevents the decaying of current. So then what would be the direction of the induced current in the coil? It is in the same direction as the source of current. Any decrease induces current to oppose the decrease. That is the direction of the induced current. That is what, in accordance with the Lenz's law, any change produced will always, so induced EMF or induced current in the coil produced will always oppose the change taking place in the same circuit or other circuit. That is known as the concept, it is all based on the Faraday's law as well as Lenz's law, induction. So same thing here, what I said in the mathematical form, L we have 82. So L stands for your coefficient of self-conductance. So let us understand or in detail the definition for coefficient of self-conductance. Write the equation on the equation, recall this equation, same equation here. Goes minus shows the direction in which it is producing, in the opposite direction to the applied EMF. Minus stands for, and for definition write L, this equation, when di by d theta equals 1, L equals E. There is a definition. What is self-inductance? Self-inductance is E. What is E? Induced voltage in the circuit. It is the amount of voltage induced in the circuit when unit rate of change of current taking place in the same circuit. What is unit rate of change of current? That is rate of change of current. So current changes with time equals 1. So it is 1 ampere per second. If the current changing is 1 ampere per second. It is a unit current change. In the circuit, the change in current is 1 ampere per second. 1 ampere of current changes in 1 second. The amount of EMF induced in the current, it is said as, it is called as coefficient of self-inductance. Definition. Coefficient of self-induction. And this is the equation to define what is coefficient of self-inductance. Let us see that there is one more mathematical equation for L, self-inductance. It is directly depends on the parameters of the coil. That is the geometrical parameters of the coil. This value depends mainly on the geometry and size of the coil. Let us understand what is that mathematical equation. This equation, as you know, flux for a coil for one turn, AB cos theta. A stands for area of the coil as one turn, and B is a magnetic field passing through that coil. And cos theta, theta is angle between area vector and magnetic field vector. I am recalling this equation. When theta equals 0, it becomes AB. Since in this magnetic vector and area vector are in the same direction, theta equals 0. This is for one coil and this is for one turn. That coil has n number of turns. Then what would be the magnetic flux? N into pi. If you multiply, you have to multiply this by n and also this n. And n pi from the equation. What is n pi? L into I in terms of L. It is in terms of pi. Let us see this flux in terms of L. Coefficient of self-inductance. Li is equal to this. Let us substitute for B, that is a magnetic field passing through the coil, in terms of current. Already equation we have derived this equation. Let me recall this equation. Magnetic field passing through this coil, it depends on the amount of current. That is mu naught Ni. What is mu naught? Magnetic permeability of the vacuum. I is the current, strength of the current flowing through the conductor. N, what is N stands for? Number of turns per unit length. Small n. Here I am putting symbol small n. Number of turns per unit length. It is same as N by L. Total number of turns divided by the total length gives the number of turns per unit length. Substitute this into the equation, you get this equation. Simplify. I left hand side, left hand, right hand side, I cancels. Write the remaining. And substitute for n. What is n? N by L. N into n, n square, A mu naught by L. What is mu naught? There is a vacuum inside the coil, that is magnetic permeability for the vacuum. Suppose if you replace, that is inside the coil, if you place something, or if the wire is wounded over a metal, any metal having high magnetic permeability like magnet, that is iron, then you can replace mu naught by mu. What is this mu? Magnetic permeability of the iron, if there is iron like this. Mu equals, look at the final equation. N equals n square into A into mu divided by L. What is N? Total number of turns in the coil. What is A? Area of the coil. That is the area of the coil. Other smaller area or bigger area, like this. So L depends on the area of the coil. Bigger the coil, that is wider size of the coil. Wider the coil, larger the value, and higher the number of turns, larger the value, and indirectly proportional to L, longer the length, lesser the value, and also depends on mu. What is M? Magnetic permeability of the material over which the wire is wounded. Iron, is that iron? It has a high magnetic permeability. It also depends on this value. So higher the value, higher is this. Higher the value, higher is this. Higher the value, higher is this. And also, if you take the n square, is now n by L. This becomes n in the numerator. Replace n by L as n. N also depends on this small n. What is n? Number of turns per unit length. If that increases, when you wind the wire, when the wire is wounded tightly over the metal, in that tight wounding, the turns are closely associated. If they are closely associated, that will increase the value of L. So all these, what is the parameters? It is depending on the geometry of the size and geometry of the coil. Bigger the size and geometrical shape, it is turns and number of turns. So value of L is a specific value of the coil. What is induction? That is called induction coil. This is also called as now induction coil. It depends on the size and geometry of the induction coil. All these parameters are important. Constant. Once it is made, this remains constant. So it may have higher or lower value, depends on the geometry and size of the coil. That is what mathematical equation to represent the L. And let us see finally units of L. To write the units of L, you can take, there are two equations. The one is equation in this form, one is differential equation. Any one you can use to write the units of L. You can use this equation or this equation. Look at this. If you write this equation, L equals n pi by I. What is n pi? Flux. Total flux is ms flux. The unit for flux is Weber. And this Weber also, this basic units, voltage second. Weber as a basic units, voltage second, voltage into time. And numerator high, current ampere, unit of current is ampere. So unit is Weber per ampere, Weber per ampere. And also this also possible. If you write Weber as voltage second, volt second per ampere, L unit. If you use this equation, you get the same thing. E is equal to L into di by dt. So L equals, write this L equals E divided by this. Take it to numerator. You know, unit of E, induced EMF unit is voltage, that is volt. Di by dt is current divided by time. Ampere per second, ampere by second. If you take them to numerator, second per ampere. V, volt second per ampere. Volt second per ampere is a unit of L. And all these units together, it is called as a special unit called Henry. He was a scientist. He was a physicist in electrical concepts. Henry H. So what is Henry? Volt second per ampere. And finally, let us understand the meaning of Henry. What is 1 Henry? What is 2 Henry? What is 0.1 Henry? Meaning. Use the same equation. L, unit of Henry, that is a special unit, is same as this. So L is Henry. Unit of E is volt. Unit of derivative is ampere per second. It is high ampere per second. Rate of change of second. Look at this equation. In this equation, let us maintain denominator always 1 ampere per second. That is ampere per second as 1 always. Then H equals V. So H equals means you can write 1H, it becomes 1V. If you write 2H, it becomes 2V. If you write 0.5H, it becomes 0.5H. If you write 100H, 100V. If you write 0.1H, 0.1V. But this always remains constant. So with this you can define what is the meaning of 1 Henry. 1 Henry is what? 1 volt of EMF is induced in the coil, induction coil, when there is a change of current by 1 ampere per second. The rate of change of current by 1 ampere per second. If that happens, whatever the amount of voltage induced, it is same as 1 Henry. That is Henry. If it is 1 volt, 1 Henry. If the coil, the induction coil in which the current changes, that is 1 ampere, if the current changes by 1 ampere in 1 second, suppose 2 volt is induced in the coil, it is called as 2 Henry. Suppose 0.5 volt is induced, it is called as 0.5 Henry. What is Henry? Henry is the voltage induced in the induction coil by unit rate of change of current, 1 ampere in 1 second. If the current changes by 1 ampere in 1 second, whatever the amount of voltage induced in the current is called as Henry. If 1 volt is induced, it is called 1 Henry. If 2 volt is induced, it is called 2 Henry. 0.5 volt is induced, it is called 0.5 volt. That is the definition. So if you go too deep into that concept, they understood what is the meaning of Henry, what is the meaning of coefficient of self-inductance. It is called as induction coil because we are using this in electrical circuits most commonly. It is known most of the electrical circuits. So with this you have completed. Thank you.